Okay, today we're going to start a whole new topic, which has always been one of my very favorites in mathematics. It's the area of sequences and series. Okay, two words to begin with an S. We'll begin by talking about a sequence. A sequence, I've got a bunch of them over here as examples, which we're going to be looking at in a minute. It's just a collection of numbers in order, like this one right here, 1, 2, 4, 8, 16, 1 1/4, 1 9th, 1 16th, 1 25th. Okay, you need some way to be able to express these things in general. And anyway, let me first define what a sequence is, and then we'll get to those specific ones. So a sequence is just a function. A sequence is a function whose domain, that is the values that you stick in, is typically the set of natural numbers or the set of natural numbers union 0. Okay, quite often with sequences, the values that you stick into the function, remember what a function is? A function is just a machine where you stick numbers in and you get a number out. And so typically the numbers that you stick in are either the natural numbers, which are 1, 2, 3, 4, 5, or else you start at 0, 0, 1, 2, 3, 4, 5. You do sometimes have sequences that start at, -10, or you might have ones that take on all the negative values and so on. But typically this is the situation. So that's all it is. And so you can write it just like you write any function. F of n is equal to n squared would be the sequence where you stick in a natural number, and what does the function do? It squares it out. So if you stick in 1, you get out 1. If you stick in 3, you get out 9, and so on. We often use n instead of x because x is typically used when we have the whole continuum of real numbers that we're throwing into the function, whereas we'll use one of the letters from the early part of the alphabet, such as N or M or I or J or K. Those are the ones that we typically use when we're talking about sequences. There's nothing that says it has to be that way, but that's just kind of the way that people generally do it. So, take this as an example. If I wanted, or let's take this as an example. F of n is equal to 1 over n, okay? So there's one where you stick in 1 and you get out 1. You stick in 2 and you get out 1/2. You stick in 3 and you get out 1/3, and so on. Those are the values. So you could graph it just like we graph any other sort of function. This could be your domain here. Here's 1, here's 2, here's 3. Notice, by the way, this is one where we'd have to start at 1 rather than at 0. Agreed? If you start at 0, the first one doesn't make any sense. 4, 5, and so on. And so what does the function look like? Well, if you stick in 1, you get out 1. Here's 1 right there. If you stick in 2, you get out 1/2. Stick in 3, you get out 1/3. Stick in 4, you get out 1/4. Stick in 5, you get out 1/5, and so on. So the sequence would just be a collection of points on your XY axis system. And so that works. It's kind of a wasteful way to draw a sequence because you're using up the whole board for just a collection of points. So quite often you want to be able to draw a sequence with less area space devoted to it than this. So instead of writing it like this, what often is done instead is you write it like this. You realize that the numbers going in are 1, 2, 3, 4, 5, so it's not like you have to write them down, and instead you might put a 0 right there, and here's 1. And so here are the values that come out of the sequence. So here, the values that came out were the values along the y-axis. Here I'm just going to put them along the x-axis. So the values that come out are going to be 1, 1/2, 1/3, 1/4, or you might use ticks rather than dots like this. And then, of course, that's not enough information. here you know that they're getting less as you go. Here, in order to indicate what's going on, you might put a little arrow there to indicate that the sequence is taking on these values here and heading down towards 0. So if everyone understands kind of what's going on, this is the way you often typically write picture a sequence. Okay, so anyway, that's all it is. So again, since a sequence, it's understood that what the domain is, instead of writing it like this, we often write the function like this instead. Notice that by writing this 1 over n going from 1 to infinity, I include all the information I need in order to be able to understand the sequence. What's happening? The domain is everything from 1 to infinity. Those are the values that you're sticking in. And then the numbers that come out are what you get by, 1 over 1, 1 over 2, 1 over 3, and so on. Okay? So instead of writing a sequence like this, we usually write it like this. We put braces around it and put the whatever it is you're doing to the n, you put that inside the braces. So there we go, very good. So here are some sequences I want us to look at for a while. Here's the sequence 1 over n squared, and for each one of these I could put n equals 1 to infinity because I'm starting with 1 on that one. Here notice it's negative 1 to the n. Here I'm starting n going from 0 to infinity. So you can tell by what numbers I have there where I'm starting. Here n would also go from 0 to infinity. Agreed? Because 2 to the 0 power is 1, and so on. So there they are. And I might as well finish them off. So here's 2 to the n. 1, 2, 4, 8, 16. This is negative 1 to the n, so that alternates between 1 and negative 1 over and over again. This is 1 over n squared. Here's 5 minus 1 over n. So 5 minus 1 is 4. 5 minus a half is 4 and a half. 4 and 2/3, 4 and 3/4, and so on. Here I have negative 1 to the n over n. So two things are happening. The values are getting smaller and smaller in size, and they're also alternating in sign. See that? So that's that one. Here's kind of the flip. They're alternating in size, but they're getting bigger as you go. Negative 1, positive 4, negative 9, positive 4 squared, negative 5 squared, and so on. And then this last one, I couldn't even write a formula for this. It would be too cumbersome. Instead, I'm just writing it down and hoping that you see the pattern. And in this case, I'm going to tell you the pattern so that you will see it for sure. But here's what I'm intending. You take the first two powers of 2, so 1/2 and then 1 over 2 squared, which is 4, and then I throw in the first odd digit after 1, which is 1/3. Then I continue on with this. So this is 2 squared, this is 2 to the cubed and 2 to the 4th, so 1/8 and 1/16, and then I grab the next odd one, 1/5. Then I continue here again. What's next after 1/16? It'd be 1/32, 1/64. Then I grab the next odd one and continue on like that. Okay? So there's a bunch of sequences I want to look at. So given those sequences, I wanted to find some terms which you're familiar with already from functions in general, but now we're going to talk about them with regard to sequences. A sequence is said to be increasing. If every term is greater than or equal to the previous one. Notice I'm allowing it to be equal. So the sequence 5, 5, 5, 5, 5 would be increasing since each term is greater than or equal to the previous one. By the way, I guess I should say right here, here's the general way we write a sequence then. We write a sub n, n going from, say, 1 to infinity, which is going to be what? A sub 1, a sub 2, a sub 3, a sub 4, and so on. So there's your typical sequence, where you're just taking on these values as n goes from 1 to infinity. So as long as each one, as you go along, is greater than or equal to the previous one, the thing is said to be increasing. it is strictly increasing. Strictly increasing if a sub n plus 1 is strictly greater than the previous one. So it's strictly increasing as long as each one is greater than the previous one. Okay? Same thing for decreasing. A function is decreasing if a sub n is greater, yeah, that's fine. If a sub n is greater than or equal to a sub n plus 1. So in other words, this one is less than or equal to this one. So I'm just thinking, you know what? I kind of like writing it like this better. I like emphasizing the fact what's going on. A sub n plus 1 is greater than or equal to a sub n. I like that way of saying it better. This one is greater than or equal to the previous one. Here we just say a sub n is greater than the previous one. A sub n plus 1, rather. Here we'd say what? A sub n plus 1 is less than or equal to the previous one. And then strictly decreasing, if a sub n plus 1 is strictly less than the previous one. So they're getting smaller as you go. Here they're getting greater as you go. Any of these things, I'll just write it like this. Any of these are said to be monotonic. Monotonic. What does mono mean? Mono means one, and tonic means, what does tonic mean? I think it has something to do with path or direction or something like that. So the point is, it's one direction. They're all going in the same direction. They're all getting smaller, or they're all getting greater. It's only going in one direction. Okay, so those are called monotonic. Here's some other key words, okay? And then we're going to see how all these things play into this. A sequence is bounded above, said to be bounded above, if, I'm going to use mathematical symbol. This is a real common mathematical symbol, which means there exists, or there is. You can see why mathematicians would want to use it, because we use that phrase so much, and it just takes, it gives you space to do other things instead. If there exists m, a real number, such that a sub n is less than or equal to m for all n. There's another mathematical symbol we have. There's both of them. We are used quite a bit. There exists and for all n. Why don't I do that right up here, just so that you have it. This means there is, or there exists. And this means for all. Two common phrases. Okay, bounded above. So there's some number which lies above all these things, okay? They're bounded above by some value. Okay, what does bounded below then mean? You can guess it. It's bounded below if there exists some real number such that, oh, there's another phrase, such that, ST kind of, it's easier to see, such that, what's true? All the a sub n's are greater than or equal to this number. Okay, then it's bounded below. Okay? A sequence is said to be bounded if it's both bounded above and bounded below. So I could either write it like that, if it's bounded above and bounded below, or another way to write it in its own definition is if there exists some m element to the real numbers such that the size of all the a sub n's are less than m. So in other words, m, all your, well, let me draw a picture of each one of these things. So to be bounded above means that maybe your points of your sequence are like this, they're bouncing around, and you've got some m up here which is above all of them. They might go down infinitely far, but they're never going to get up beyond this point. That's bounded above. To be bounded below means that there's some m down here where wherever they might bounce around, they're never going to get below that certain point. And then to be bounded means it's bounded above and bounded below, which means that basically they're captured between negative m and m. So here you have a negative m, here you have m, and all of the a sub n's are bounded between those two. If this is the case, that means that a sub n they're all between negative m and m. So they're captured on both sides, both from the left and the right. Okay, that's what it means to be bounded. Okay, and finally, one other word is convergent. A sequence is said to be convergent if the limit of the sequence exists. If the limit of the sequence exists, okay? So what does it even mean for the limit to exist? Well, we're gonna get to that, but I'm guessing you have kind of an intuitive notion of it already. And so let's kind of see once if we all agree on these things, and then we're going to dive into this one in more detail by way of a definition. Okay, so let's check each one of these and see which ones are increasing. Okay, which ones are increasing? Let me use some other chalk here to indicate which are which. This one is which ones are increasing? So they're getting bigger as they go. This one would be, right? I'll use an I right there. That's increasing. This one is increasing. This is where I really kind of wish you were all here right in my kitchen with me, because this is where a lot of feedback is important. Okay, this one's not, this one's not, this one's not. Okay, so those two are increasing. What about and in fact they are strictly increasing as well. What about decreasing? Are there any that are decreasing? You go ahead and look at them while I grab another color here. Decreasing. It looks like this one is. Agreed? This one's decreasing. Is that the only one? I think so. Okay. Which ones are monotonic? There's monotonic. Well, monotonic, it's either increasing or decreasing. So I could put an M right there, and an M right there. Those are monotonic. None of the others are. Agreed? Which ones are bounded above? See how many more colors I have. Bounded above. So there's some number which lies above all the terms in the sequence. Do you agree this one's bounded above? It's bounded above by 17, for example, right? All of these things, none of them are any bigger than 17. Okay, so this is, I'll put an A for bounded above. This one's bounded above, right? None of them get above 7. Also, none of them get greater than 1. But I'm just pointing out that there's lots of things that they're greater than. This one, it's not bounded above. This one, none of them are going to get bigger than 5, for example, right? So bounded by 7, by 5, or by 8, or whatever. So I'll put an A there. This one is bounded above. None of them are going to get greater than 5. This one's not bounded above, right? It's going to be 16, and then it's going to get up to 36 and so on. That's going to keep going. This one's bounded above. Right there. Okay? Which ones are bounded below? So I have yet another color. Here's a pink right here. So bounded below. This never gets below 0. I'll put a B for that. This one's bounded below. Okay. This one is bounded below. This one's bounded below. Nothing's going to get less than 0, for example. This one's bounded below. Nothing's going to get less than -1, it looks like, as an example. Not this one. Agreed? This one, they're going to get you're going to get negative numbers that go down forever. This one's bounded below. Nothing's going to get less than 0, and so on. Okay, let me make sure that my computer's still working. Yep, very good. Okay, so you've got that. Okay, now finally convergent. Okay, convergent. What does it mean to converge? It means the same thing that if a function converges, right? It keeps getting closer and closer and closer to some value. And that's exactly what we're going to spend time, what do we really mean by that? But this is where it'd be good to have everyone right here in the room. But do you agree that this one right here looks like it converges? Now, let's see, I guess I can use I'll use a C for convergent. I think that's all the colors I've got. I've already used green. Okay, so I'll use oh, blue. Nope, I've already used blue. Okay. So convergence. So this one right here, I'll put a circle around it just to differentiate it from everything else I have drawn there. C means convergent. This thing right here, they're getting closer and closer to 0. This thing right here, would you agree that it's not converging? It's bouncing back and forth between 1 and -1. So that's true, but if you're asking for one particular value that it keeps getting closer and closer to, you'd say no, it's not. Okay, so we'd use the word divergent then. This one here, there's no real number that it's getting closer and closer to, so that wouldn't be the case. This one here, they're getting closer and closer to 5. Agreed? As n goes out larger and larger, they're getting closer and closer to 5. So that one's going to be convergent. This one is getting closer and closer to 0, right? If we were to draw a picture of it, what happens? Here you have 0 right there, and you start at -1, and then +1/2, -1/3, +1/4. They're going to be sneaking in on both sides of 0. So that one's convergent. This one here is about as wild as you could imagine. It's going off in both directions, right? It's going to -infinity and it's going to +infinity. So that one certainly isn't. Now what about this last one? That's kind of an interesting one. What happens to that? It's 1/2, 1/4, and then it jumps back up to 1/3, then an 1/8 and a 1/16, and it jumps back up to a 1/5. Okay, this is where, as I say, I really need your input here. I kind of want to know what you're thinking. So here's 0. So let's look at them again. Here's 1/2, then 1/4, and then and then it's 1/3. And then you get 1/8 and 1/16, and then you get 1/5. And then you get what? 1/32nd, 1/64th, and then you get 1/7. And then 2 more that are really close, and then you get maybe this one right here. So do you agree that eventually all the terms are getting closer and closer to 0, right? Some of them are taking longer than others, but eventually they'll all be close to 0. And so this one here, we'd also say converges to 0. Okay? So before we go any further, let me give you a definition of what it means to converge, okay? And then we're going to look at the relationship between these words, okay? So let me just say here. Here's a definition. We say that this sequence converges if the limit of a sub n, let's say this, if there exists an L, which is going to be the limit, such that the limit of a sub n as n goes to infinity is equal to L. I'm going to break this up into two parts. We'll say a thing converges if there exists an L such that the limit as n goes to infinity of a sub n is equal to L. So I'm going to say that, and then I'm going to say that. I'm going to say this. Limit of a sub n as n goes to infinity equals L. What does this mean? Because just to write that, I haven't given it any meaning yet. Okay, here's the precise meaning. Means, here's what it means. Given epsilon greater than 0, there exists a capital N, which is a natural number, such that if n is greater than capital N, that implies that the distance between a sub n and L is less than epsilon. Okay? Now, this would be a great thing for you at this point just to shut off the video and keep this thing showing and take some time and see once if you can understand what that's saying. Here's what it's saying. Let me draw a picture right here. We say that a sequence converges to L, right there. Let's say that's L, and say we have a sequence of points that are bouncing all over the place, okay? What does it mean to say that sequence converges to L? It means you give me any epsilon. Typically, you think of this as a small number. I mean, that's the power of the definition is you're saying no matter how small of a number you choose, like, okay, once you choose it, you can just think of making a little interval around L of that size, okay? You give me a little epsilon, and then once you give me an epsilon, I'll be able to tell you that if you go out far enough in the sequence, okay, so here's a sub 1, a sub 2, so way out here in the sequence might be a sub capital N. And then beyond that is a sub capital N plus 1, and you go on like that. But way out here in the sequence, there's some term, a sub capital N. There exists some capital N such that as long as you're beyond that point, so as long as you're beyond this point here, all of the rest of the terms in the sequence are going to be within epsilon of this L. Okay, they're all going to be within epsilon of L. So in other words, you choose how close you want them to get to L, and I'll say, okay, if it converges, I'll be able to ensure they're that close eventually. Okay, eventually they're all going to be that close. That's the idea. So this thing converges to 0. Why? Because eventually, no matter what little interval you give me around 0, do you agree? Eventually, all the terms of that sequence are going to be inside that little interval. This thing, there's no way it can have a limit, right? Because here's your negative 1, here's your positive 1. What could possibly be a limit? Could 1 be a limit? No way. Because there's no point in the sequence where eventually everything will be inside here. If I chose my epsilon to be this big, then everything would be inside here. But this has got to be for any epsilon. Given any epsilon greater than 0, you've got to be able to find an n. And if I choose my epsilon that big, there's just no way to do it. There's no way, there's no point in which all the terms will eventually be inside. Okay, let's look at the other ones that we claimed converged. We claim this one converged to 5. Why is that? Well, here's 5 out here. They're climbing up like this, right? So you give me a little interval around 5, and yeah, sure enough, eventually all those things are going to be that close to 5. Okay, we said that this one converged. Let's see if it jives with our understanding. Here's 0 right here. What are these doing? They're bouncing back and forth like this. See that? Is it true? Do they converge to 0? Sure enough. You give me any little interval around 0, and eventually all those terms are going to be inside there, right? Never to come back out again. And finally, this last one, let's see once why this one converges to 0. Because what happens? Here's 0 right here. Here's a little interval around 0. What happens? You start at 1/2, 1/4, and then 1/3. 1/8, 1/16, and then 1/5. Now you're inside here. Boom, you're back out again. Does that mean it converges or not? Sure, we just haven't gone far enough. You can bounce back in and out a few times. That's okay. It's just that eventually you're going to be in there for good. A couple more, now this one. A couple more, now this one. A couple more, now this one. And from then on, everything is going to be inside there. See that? So there's another example of one that converges. So this is I always like my classes to spend a lot of time thinking about this definition, because in fact I have them try to give a definition of limit on their own first, and then whatever they say I show how it's inadequate. If they just say closer and closer, well, all of these are getting closer and closer to 7, right? They're getting closer and closer to 7, but it's just that they're not getting arbitrarily close to 7. So you have to be really close. You have to be really careful with the words you choose. Okay, very good. So here's the next thing I want to do. I can see just by my amount of time here, I'm going to have to break up this lesson into 2 lessons, which is fine. So let me write Convergent again. Okay, here's the next question. Which of these things implies the other? We have 3 key words here. The 3 key words I want you to consider are these ones right here. The word bounded, the word monotonic, and the word convergent. Okay, let's find relationships between these things. So here's what we're going to fill in. If the sequence AN is blank, then it is blank. You have different combinations of these to put in here. Which ones make it true? Let's put them in order here. Monotonic, bounded, and convergent. Let's start with monotonic. If a sequence is monotonic, does that mean that it's bounded? If it's monotonic, does that mean that it's bounded? Okay, you try to answer before I answer. The answer is no. Here's one which is monotonic, agreed, but it's not bounded. So the answer to that one is no. So if it is monotonic, then is it bounded? The answer is no. Okay? Let's do the next one. If it is bounded, if it is monotonic, then is it convergent? Just because something is monotonic, is it convergent? No. this same one applies here again, right? It's monotonic, but it doesn't converge. So the answer is no. Okay? Try to keep up with me. How about bounded? If it is bounded, then is it monotonic? If it is bounded, is it monotonic? No. Here's one that's bounded, right? But it's not monotonic. Here's another one which is bounded, but it's not monotonic. So the answer to that is no. Next one. If it is bounded, is it convergent? If it is bounded, is it convergent? Well, no. This one right here is bounded, but it's not convergent. So the answer to that would be no. Okay? Finally, let's put this one here, C. If it is convergent, then is it monotonic? I want to make sure that you're still within sight here. If it is convergent, is it monotonic? Just because it converges, does that mean it's monotonic? Can you stay ahead of me? If it's convergent, does that mean it's monotonic? No. This one right here is convergent, but it's not monotonic, right? Bounces back and forth. So the answer to that is no. Keep track of all my notes. Okay? And I think we just have one left. If it is convergent, then is it bounded? Let's look at examples. If it is convergent, then does it have to be bounded? If it is convergent, does it have to be bounded? What do you think? We don't have any examples of things which are convergent but not bounded. So it's not clear from our list of examples here whether that's true or not. Is that true? If something is convergent, does it have to be bounded? Well, for sake of space, I had no choice but to take off the definition of what it meant to be convergent. But let's think about it. Let's just think about it. To be convergent meant what? It meant that you had a limit, and it meant that eventually everything was inside of a little neighborhood around that limit. Eventually everything was inside there, right? Not necessarily right away, but eventually. Let's think about it. Since eventually everything is going to be inside there, past a certain capital N, everything is inside there. Here's the key word. You only have finite number of things that are outside of there. They might have bounced all around. They might have been like crazy. Boom, boom, boom. But eventually they get trapped inside there, and they're going to be inside there forever, ever after. See that? You only have a finite number of things outside. And since you only have a finite number of things outside of that interval, we can just look at each one and say, okay, what's the smallest of all of them? And put a bar right there. And what's the biggest of all of them? And put a bar right there. And basically, you got them trapped. Either they're trapped by this thing, maybe they're all on this side, in which they're trapped by this side of the little interval. But either if they're all coming like this, they're all trapped from here, or maybe you have some on both sides. But the key is you only have a finite number of them. So either way, they're trapped. And so this is the case. If it's convergent, then it's bounded. Okay? If it's convergent, then it's bounded. Very important. So again, for the sake of space, I can't write this all off in its own. So very good. One more thing I want to do now. I want to ask, what if we have a sentence like this? If an is blank and blank, then it is blank. Okay, let's put in different combinations here. Let's start with, if it is bounded and convergent, then is it monotone? Is that true? If it is bounded and convergent, then is it monotone? No. This one right here is both bounded and convergent, but it's not monotone. So that's not the case. Okay? If it is bounded and monotone, I want to take monotone and convergent. If it is monotone and convergent, then is it bounded? If it is monotone and convergent, then it is bounded. Is that the case? Yes, we just proved it. We don't even need monotone. We know that if it's convergent, then for sure it's bounded all by itself. So this is true without even needing this one. So the answer is yes, that's the case. That's kind of trivially true. Okay, because we already proved that it was true. What's the last one? If it is monotone and bounded, if it is monotone and bounded, then is it convergent? There's one we haven't thought about yet. If it is monotone and bounded, then is it convergent? For sake of space, I'm going to just go ahead and erase this now. Almost done with the talk. So I think I can safely get rid of this. And let's draw a picture to illustrate. It's monotone and it's bounded. So here's our real line, and say it's bounded between negative m and m. Okay, so everything in the sequence has got to be, make sure I'm still being shown here. Yep, very good. We're between those two, we're bounded there. Now, we're also monotone. If we are monotone, does that force us to be convergent? Let's think about it. Suppose if we're monotone, that means we're either increasing or we're decreasing. So let's assume without loss of generality that we're increasing. Okay, let's think about it. Well, can you kind of see the trap we're in? We don't necessarily have to go all the way up to here. Say we never get farther than here. Okay, we're bounded by this, but we might be bounded by other things as well. So the point is, if we're bounded above, there's going to be some smallest thing which is also bounds us above. It's called the least upper bound. If we're bounded above, then maybe that's our least upper bound, or maybe there's another upper bound which is smaller than that. But there's this thing here is called the least upper bound, which is the upper bound, which is the smallest possible one. And what happens as you just keep climbing? You have no choice but to go forward. Okay? If this right here is the smallest upper bound, then if you make yourself a little interval, a little epsilon interval around there, then this is not an upper bound, which means eventually you're going to be inside there. And as soon as you're inside here, you are trapped. Because if this is the smallest upper bound, if this indeed is an upper bound, you can't go above it. You can't get above that thing. And since you are monotone, you can't go back outside. So you are trapped in here forever. And sure enough, given this little epsilon here, you are always going to be beyond a certain point within that little epsilon neighborhood. If I made my epsilon even smaller, you're going to be eventually trapped within there. Okay, so this one is the case. If something is both monotone and bounded, it has no choice but to be convergent. So that's really an important theorem right there, because that's one way to show something is convergent that you wouldn't otherwise know. If you can just prove it's both monotone and bounded, you can prove then, or we have proved that it's convergent. Okay, that's a whole lot of stuff, and I'm going to do another video in which we're going to look at some other sequences and actually see how we can evaluate the limits, find out what they converge to, and then we'll go on from there. Lots of good stuff here.